All right, so I got everything being recorded now. So there are a few things on this list here. The first one is simply an announcement of we're going to have exam two next Thursday. So 1 week from today, we have our exam two. Okay, so you got 1 week to study and get ready. The exam from last semester is already linked from the announcement, so you can download it so they can have your view on the exam when I work out the exam answers. The second one is a link to a resource that the district, the LRCCD, the Los Rios Community College District, that is organizing. So they are using. Unfortunately, they all fall on Thursdays. Let me click on that link and show you what it is. Okay, so if you scroll down just a little bit, the three events are Emotional Wellness Toolkit for Finals. And the first one, which is for today, is about self care and time management. The second one, which is next Thursday, is about understanding and applying motivation. And then the last one is test taking anxiety or how to cope with test taking anxiety. And if you look at the time, unfortunately, it does overlap with our lab. Not a whole lot, okay? It just overlaps, for about 20 minutes. So if you can get your lab done early, then you will be able to, kind of watch, join the sessions and see what they have to say. Now, I have no idea what they're going to say, okay? This is just a link that I got from the district. Um, so anyway, if people think this might be helpful or just curious, okay, I might actually just watch it just out of curiosity. But this is a resource. That's all I'm gonna say. And you can change. You can see I changed my Firefox background to a Doctor Who theme. All right, so now we are gonna go get the exam started. So I want to show you what the exam looked like from last semester, and then we're gonna go through all the answers. Now, this one was not designed for paper-based exams. So I'm gonna have to make some adjustments. So do not be too concerned about, how much stuff you have to type or write, because your exam is going to be paper-based and using a writing instrument to kind of record your answer. So here we go. This is from last semester. So the first question is about analyzing a circuit. So we have to kind of analyze how a circuit is built and also how it behaves as we change the input pins. We have done that in this class already, okay? But I'm going to go through this question just to show you, how I would answer this question using what we have learned in this particular semester, because I changed the way this is taught, every semester just a little bit. So I think this semester we have the best way of representing, how to track all of those changes. All right, so the question starts with the usual stuff. It starts with the usual discussion of, what is in the circuit and also how, those components are connected. I really do not want to give you a diagram, to show you how the components are connected, but you are more than welcome to kind of draw the circuit, during the exam so that you can, if you're visual, that will help you, understand what is connected to what else. Is that okay? All right. So the question is asking you, start with, B equals to 1, X equals to 0, and then we want to analyze the circuit to find out what exactly is going to happen when that is your initial condition. And you also have to assume that you know nothing about the state of the devices. So everything is unknown or a question mark unless we can confirm it after we get, after we propagate the changes because of the input pins. Explain your answer in NC-PD phases. NC is node connectivity. It updates the input ports of devices based on the change of an output or the given value of an input pin. PD, which is propagational delay or a propagational change, updates the output ports of devices based on the changes of input ports of the same device. Last semester I gave people a table so they can start with this one. This semester, I think I'll do better. Okay, I'll do something better, and I'll show you what I mean by that in just a few moments. So do we have any questions about the questions up to this point? Yep.
Will you give us the thing with colors?
Well, that's my intention. I will give you, something that is in color. So if anyone is colorblind, you might want to let me know ahead of time. So this way I can choose the correct colors so that it's easier for everybody to see. Okay? All right. So back to the description of the circuit. I know some of you are really big on I need to see the circuitry in order to do the work. But let me propose that we only use the color coding, okay? Because I think that really is a better way to do it. So let me show you what I have done so far with color coding. And let me just kind of put this on your screen. All right, so this is just an overview. I know, to the people in the back, your handwriting is going to be a little bit hard to read. So I'm going to zoom in as we, start with this. Um, I kind of like this for many reasons. One is it reminds me of Skittles. I like Skittles. um, and the second one is I really think it's easy to follow. Okay, so we'll get started, and you guys can kind of let me know whether you agree with me or not. All right, so we're going to go ahead and get started here, and I will do this only using the color-coded columns without referring back to the actual description of the circuit. So we'll see how that goes. All right, so you can always switch on your screen to only look at the exam question. So this way you can focus on the question itself. I kind of have to go back and forth a little bit. So this is the initial condition. B is 1 and H is 0. So I go back here, and the first thing is I have to locate where is B and where is H. So B is over here, and H is all the way over here. So let me zoom in first, so this way it's easier for you guys to see what's going on. And I need to go back to my actual Zerno screen on this side and change the stylus input to accommodate for this screen size. So give me a second to do that. All right, so I got my stylus working, and we can now zoom in maybe twice or so, okay? At least it'll get it to the point where I can comfortably write on the screen. All right, so we start with the pins, the input pins that are given to you. So in this case, maybe zoom in like one more level, okay? All right, so we know input pin B is going to start with a value of 1. So let me change the tool, get rid of the line drawing tool, back to pencil. So we know this is going to be a 1. Oh, okay, why is it not writing? Oh, yeah. Oh, that's right. No, it's not highlighting. I put it into pencil mode. Um, what did I forget? Okay. Hmm? Mm, yep, you're right. Okay, what's the color? All right. So we have a 1 here because you can. I also changed the way I capture the screen so you can actually see my stylus before I write. So it's right here. We put a 1 here. Now I put an underline under it because it is a change. Because it's a change from what used to be just unknown. And the same thing is going to apply to H, which is also an input pin. So the H input pin is over here. I also put a 1. Oh, that's supposed to be a 0. Okay, so put a 0 here, and put an underline under that because that is also a change. Everything else are unknown, so they're all going to be question marks. So I'm going to try a different way to do this today, which is if they are the same as before, I don't even write anything. So this way we can save some of the writing. But initially, I should probably still put question marks on each item so it is clear to us which ones are unknown at this point. So we have a whole bunch of question marks. Okay. So this is the initial part of step 1. So the next one is going to be an NC, which means we are using the node connectivity so that we can spread the changes to everything of the same color. Okay, so NC is about quote unquote following the rainbow. Okay, which is a slogan mark of some commercial. I cannot remember what it was. Was it Skittles? Okay, well, that commercial definitely worked on me. So now we have to follow all the yellow lines because all of those are going to be updated to ones. So this is a 1, and this is updated to a 1, which means we have to put an underline here because I need to track it later on. All right, so that takes care of all the yellow ones, and now we need to look at the gray ones because the input pin H is gray in color, so everything else that are also gray in color should be updated at this point. This one is not going to getting underlined anymore because I've just spreaded the change, but this one is going to get an underline, and this one is also going to get an underline because that is the change. Everything else remain as was. So that completes the first NC, the first node propagation. Then the next phase is PD, which is propagational delay, or after a propagational delay. Now we want to find out um, what devices can potentially output something different because at least one of its input got changed. Was that sentence understood, or does anyone want me to further explain that? I need to look into devices where at least one of its input pins has changed so that we can evaluate whether the output should also change at this point of time. Okay, so how do we know? Well, we can know because we can see we look at all the underlined ones. Okay, all right. So this is an input pin, which is not a concern. This one here is an input pin of an AND gate, and it's getting a 0. So the question is, can we make any conclusion here about the output? In other words, can I, put something over here? Do we know conclusively what the output should be at this point? Even though well, actually, both of his inputs are known now, so we should be able to figure out the output. So what should be the output of this AND gate? It has one input being 0 and one input being 1. It should be a, no, this is not a NAND gate. This is an AND gate. It is not a negated AND gate. We are looking at false and true. What should that be? It should be false. Very good. Okay, so we put a 0 here with the underscore underneath because we have just changed something from unknown to not only known, but definitely a false. Okay, very good. So now we move on to this particular NOT gate here, and we ask, well, if we know the input of the NOT gate is a 1, is that enough for me to make a conclusion about its output? What do you guys think? And it should be a 0. Okay, very good. And now we look at the next. This is an input pin, so it's not a concern. This is a NOR gate. None of the input is known at this point. This is an AND gate. We know one of the input is a 0. So is that sufficient for me to come to a conclusion about its output, which is here? This is a AND gate. It has 2 inputs. So we are looking at something like some unknown and false. Can we do we know the result just because we know one of the pins is a 0? Yes? Okay, so what should be the output? 0. Very good. All right. So that concludes the propagational delay phase of analyzing the circuit. But let me ask, are there any questions about how we came to the conclusion that we have arrived, for this particular propagational delay step? Yep.
So just that I make sure I'm understanding it right.
Yeah.
The out to the right of like 2 input pins is referring to like the output of whatever the gate.
That is correct. Yep. Yeah. So what I did not make very clear is these three columns, they correspond to this NOR gate. So these three all correspond to the NOR gate. These three all correspond to the AND gate. These two correspond to the NOT gate. These three correspond to the NOR gate. And then these three correspond to the AND gate. So that's a very good question, because I did not mention how the columns are arranged. All right. Any other questions? Okay. If there are no questions, then I have a question. Can we conclude that we have arrived at the steady state, which means I don't think there will be any further changes. Can we confirm that there will be no further changes at this point? Nope, because we just changed some of the output pins of some of the devices. So now I have to do another NC, which basically means, okay, let's follow the colors and update all of the other pins of the same color. So NC again. So this time we are looking at, well, let's look at the what appears to be purple, kind of ish. This one over here. So we're going to update every single one with the same color as 0. So we're going to put a 0 here and put an underscore because it is new, and that's it. Okay, we only got one that has that color. And then we look at the orange one here, and then we look at all the orange columns, and they all show they all should be updated with a 0, like that. And there's only one other one that is in orange color. And then we look at the gray one. Nope, sorry, not the gray one, but the light blue one. So the light blue one is also just updated to a 0. So now we look up all the light blue ones, and the only one that is also light blue is over here. And I think that should be it. Okay, that is the end of the NC phase, which is updating other ports because they are connecting to the same node. That's what NC is trying to do. So now we have to go to PD again. So after a certain propagational delay, now we have to reevaluate all the devices that has at least one of its input pins changed. So we're going to go from left to right. So this NOR gate just got one of its input pins changed from a unknown to a 0. So the question is, can we say something about the output for this particular NOR gate? So a NOR gate is a negated OR gate. So the first thing you need to think about is what would this be for a regular OR gate? In other words, if we know that we are saying false or some unknown, do we know the result of that expression? And the answer is no, we cannot know the answer. So that means we are not going to do anything about this cell here because I cannot make any conclusion about the output of the NOR gate. Is that okay? Does everybody understand why in this case, not knowing input pin 1 is going to prevent me from making any conclusion? Okay, very good. Let's look up another one that just got updated, which is this one here. Once again, we have a NOR gate. One of the input is known to be 0 at this point, but the other one remains completely unknown. And once again, we cannot make any conclusion about the output. And then we look at the orange one. So this one is updated from a unknown to a 0. But we already know at this point the second input of the AND gate is also a 0. And we already know the current output is 0 already. So this is also not an update because it just maintains its output of 0. And we're doing okay so far with this. So in this propagational delay step, we can now say we have reached a steady state. In other words, there are no updates to perform from the previous NC. So as a result, we can make a conclusion and say all the changes have propagated through the devices of the circuit, and we can expect no further changes at this point unless we change the input pins. Is that okay? Does everybody understand that conclusion? Yep, go ahead.
We just changed the first input on the NOR gate with the 1.
So the first input of the NOR gate
NG.
You mean the light blue one?
Yeah, the light blue one.
Okay, so the light blue one, okay, let me just get here. You're talking about this one?
Yeah.
So it was changed from an unknown to a false, but we cannot make any conclusion about the output of this NOR gate. Because it still depends on the other pin. Because if the other pin is a 0, then the output should be a 0. But this is a NOR, so if the other pin is also a 0, then the output should be a 1. But if the other pin is a 1, then the output should be a 0. But since it is unknown, I cannot tell which way it's supposed to be.
So the steady state depends only on the outputs, is what you're saying?
So the steady state is basically asking for this particular row. Let me highlight which row we are talking about. So for this entire row here, if we cannot make any further conclusions that is different from what a particular thing used to be, then we can say, there are no further changes to analyze because we have reached a point where everything is just maintained. Okay, there are no further changes. There are no further conclusions that we can make that's different from what it is currently doing. All right. So now that means that this is the answer to the first part. Okay. So there are actually 4 parts. I think I will complete 3 of those 4 parts because I need some time to talk about the other 2 questions as well. So let's take a look at what is the second step. So if you scroll down in the question, the second step is asking, what if I change B from a 1 to a 0? So that would be that's the source of the change because I'm changing the input pin, the state of the input pin. All right, so we go back to the circuit. And now we ask, okay, so this is going to be step 2. So I'm just going to write step 2 over here. And then on that row, we're going to change B from a 1 to a 0. All right? So this is reflecting you clicking in LogiSim and changing the state of an input pin. So it went from 1 now back to a 0. So the question is, what is that going to do? So the NC is going to spread out all the yellow lines or the yellow columns will also update to a 0 because they are all connected in the circuit using a node. And that's it because the other pin did not change. The other input pin, which is in H, input pin H, that did not change. So now we can do a PD. In other words, we look at all the devices where at least one of the input pins got changed. So that would be the AND gate here. So now this AND gate is 0 and 0. So the result here should be 0. But it was 0 already, and it's not a change. If it's not a change, I'm not going to write anything here. That makes it easier to track, what just got changed. All right. What about the other yellow line, which is for the NOT gate? So for NOT gate, it was a 1 for the input pin. Now it is a 0. So the output would actually change accordingly. So the output is going to change to a 1 in this case. So the propagational delay step is only going to update the output of the NOT gate, but the output of the AND gate is maintained, and therefore we do not write a 0 in that case. Do we have any questions about this particular step? Nope. Okay, so we now go for NC again. So NC, once again, is to follow the rainbow. And this time we only have to follow the color orange. So now we have this one updated to a 1. And one thing that I found was kind of difficult for me was to kind of be careful enough to figure out, okay, do we only have 2 columns that are labeled orange? But that's partially is because I'm looking at the screen over here and instead of on the piece of paper. All right, so now we go for another PD. And then we ask, well, are there any devices with at least one of its input changed? So the answer is yes. This AND gate just got one of its input, the first input, changed from a 0 to a 1. But the other input is still a 0, which means the output of a 0 is maintained. If it's maintained, I'm not going to write anything here. So that means for this particular PD, the entire row is empty. It is all blank because there is no update to perform in this case. So once again, we have reached a steady state. Is that okay? So steady state means there are no further changes that we can perform in this particular circuit. Everything should remain as is, in this particular step. All right, so now we go to step 3, okay? So step 3, that particular row is only indicating what I'm changing in terms of the input pin. So let's go back to the question, and let's see, there we go. And then we want to scroll down a little bit and find out what is the change. Well, H is changed from a 0 to a 1 in this case. So now we switch back to the analysis of the circuit, and we say, okay, so this is input pin H, and we have to find the right row, which is this one here. It's changing to a 1. And then we have an ANSI. We spread this one to all the gray columns. So we got 1 here, and then we got 1 over here. All right, then we have a PD after that, which is basically asking for all the devices that have at least one of the input pins changed, let's figure out the output as much as we can. So for this particular AND gate, it still has one of the other input pin being a 0, so the output of being a 0 is still maintained, and because it is maintained, I'm not going to write anything here for this particular cell. The other AND gate, which is over here, had one of the first input being a 1 already, and now I'm changing the second input to also be a 1 instead of a 0. So indeed, the output will change from a 0 to a 1. So I'm going to write it down here. So that means I'm not done with this yet. Okay, we are not currently at a steady state because that change to the output of the AND gate of J can potentially cause something else to change. So we are not at a steady state. So now we do an NC. We look at everything that is in light blue color. There's only one, which is all the way over here. We say, okay, that one is going to get a 1 now. I'm just scanning to make sure there are only 2 light blue ones, and I think that is correct. So now we go for another PD. So now the only thing I have to look into is this NOR gate. For this particular NOR gate, I have one input being a 1. The other input is still unknown. We have not touched the light green ones. But guess what? This is a NOR gate, so if at least one input is a 1, I know the output already. So the output is going to be a 0 in this case, and that's for this PD. So that means I'm not done yet because we have not confirmed that we are at a steady state. So we have to go for another NC and update the other purple ones. So that means this one is going to update to a 0. This one is also going to update to a 0. And then we go back to a PD. This is a NOR gate. Both inputs are known to be zeros now. So the output is also going to be known to be a 1 at this point. This is an output pin, so it's not going to do anything because output pins do not have any, there's no logic associated with that output pin. So that one we can just leave it as is. And because we just made a change to one of the columns, we are not at a steady state yet. So now we have to go to another NC, update all the green ones to 1s. So we got 1 here, we got 1 here. And now we have to go for another PD and say, for this particular NOR gate, we have 1 and 1 as input. But that's not going to change the output because 1 or 1 is a 1, and then the negated 1 is a 0. We got the 0 here already. It's not a change from before. So we don't have any entry for the green ones over here. This is an output pin. So the output pin being changed to a output of 1 also does not respond at all to a propagational delay. So at this point, we know that we are at a steady state for step 3. So are we doing okay so far with this analysis of the circuit? So I'm not sure about you because we all kind of work differently. Some people are more visual. They like to look at the connectivity in the diagram. But for me, this works really well. Okay, just matching the color works actually better than having to follow the lines, in the circuit diagram. So, but on the other hand, if you really want to look at the circuit diagram and kind of look at the wiring, um, you're going to have to kind of make that happen on your own, because there's no way for me to easily generate the diagram from the description of the circuit.
And you're gonna include like the colored bars in the
Yeah,
example? Nice.
Yep, I got the toner for my printer already. It was running a little bit low, but I think I can do it now. So I would do about the same thing, making sure that you guys can differentiate based on the color. And is this color scheme okay for this class? I mean, okay? Because I just want to confirm that this is not. Um, I did not use colors that are difficult to differentiate for some people.
I feel like yellow might not be all the best just because it's like yellow on white. But,
Oh, okay.
But that's just something that can be like easily changed.
I have some other colors that I have not used yet. Um, so if I look at the color scheme here, I think red has not been used. So instead of bright yellow, I could use red. Then the question is, okay, I can give it a try, and you guys can tell me whether this works for you or not. So I'm gonna use the red color here. Is that enough? Is it different from orange sufficiently so that you can differentiate between the red versus the orange?
Oh yeah, definitely. At least to me, I believe.
Okay.
If
The rest of
anyone
the class, any objection of using red instead of yellow? Nope.
I don't object, but it's still, I mean, it's hard for me to differentiate colors.
Oh,
So, I mean, is it possible that you just write like the initial of the color up top?
for me to
So
give
say
you the
for like yellow,
circuit?
just write Y up top. That way I can see the entire bar.
So like instead of a visual color, you write down the first letter of the color up top.
Oh, okay, I see.
No, but that's just for me. I mean, it's hard for me to see colors.
Mm, I can number the columns if that would help. So basically, columns of the same color would have the same number on
Yeah.
top. Okay, yeah, I can do that. So let me just write this down as note to self, because otherwise I would forget. So go back to pencil tool. Okay, also label using numbers for each column. All right, there we go. Cool. So now we move on to the second question. So let's go to the second question. And I can kind of do this and potentially, maximize it. So this way it's easier to read the entire thing. Yep, go ahead.
I almost forgot to ask.
Mm-hmm.
So on the exam,
Mm-hmm.
how in the step 3 NOR gate,
Mm-hmm.
how since one of the inputs is 1, it implies that the result is going to be 0 no matter what.
Mm-hmm.
Do you want us, kind of like how we did on exam 1, write on the side, like the reasoning for why that NOR gate is 1?
For this particular exam, if you produce something like this, it will get full credit already.
Okay.
Yep. But if you want to kind of as a note to self, you can add anything you want as note to self, but that would not be needed to get a full score.
Okay.
Yep. Mm-hmm. All right. So getting back to, yeah, because otherwise it would take too much time, because everything is handwritten in this test, and I don't want, your score to depend on how quickly you can write on a piece of paper. That would not be right for this class. All right, so for question number 2, I am giving you the values of the tunnels in the processor circuit in Logisim. And obviously, because it's all done on paper, you cannot use Logisim to help you. So Logisim is not going to be helpful. But what you might find helpful, or what I think everybody will find helpful, is to have a printed version of the diagram. So I would definitely, do that. Now, if you say, but Tat, can you include that in the exam and just use some of your toner? Sure, not a problem, okay? Because black toner is fairly inexpensive. It's not a big deal. Paper is not expensive either, okay? Most of the expenses of printing has to do with the toner, and the color toner is the killer. The black toner is not an issue. So yes, so I can include this diagram along with the ALU as well as the register bank in the question sheet, so that way you have a reference. But do you want to have to rely on the one that I print, to refer to the design? My answer is you might want to kind of pre-print this on your own, and then you can annotate, color code, and do whatever you need so that you can find things more easily. Okay, because it's kind of busy, right? And not everything is useful, all the time. So you might want to kind of have your own version of this so that it's easier for you to find the information that you need. Okay, so that part is up to you. I will include a picture like this in the exam itself, but it's not going to have any annotation. It really is just what you're seeing here. All right, so getting back to the question. All right, so getting back to the question, you are given the following pre-dissected microcode slides. Okay, so let's talk about what that means. A microcode slice is just the content of one location in ROM. That's basically what it is. So the question is, would you rather have me to give you the 7-digit hexadecimal number like this, or would you rather have me to pre-dissect everything so I can actually tell you what each tunnel has? So RI mux is 1 bit, RIEN is 1 bit, RISEL is 2 bits, and so on. So I'm guessing most people would like me to give you the actual value of each tunnel instead of giving you a 7-digit hexadecimal number. So you're going to have to convert that into a 26-bit pattern, and then you pick out the right thing within the 26 bits. Is that assumption correct? Is anyone objecting and go like, no, I really want the 7-digit hexadecimal number and splice everything myself? Okay, I don't see any objections. So this is the way we're gonna do it. Okay, but does everybody understand what this is representing? It is representing the output of the ROM for one particular location. And I'm asking, what is going to happen with a rising edge when these tunnels are in these states? So the question is, first, identify and list all the components that are going to be, okay, bad grammar here, that are going to be updated on the rising edge of the clock.
That's 0 to 1, right, on the clock?
That is correct. So when the clock goes from 0 to 1, what components are going to be updated? And when you look at the uh, processor like this, it's kind of daunting, okay? Especially for people who have not done the exercise that I have suggested quite a few times already of trying to single edge through the whole thing and figure out how some of the instructions operate. So for someone who has not done anything like that, this is going to be hard to analyze. We kind of know where to start, right? Because we look at all the components that can indeed be updated. So you might be asking, some people might be asking, so what can be updated? Well, the question actually gives you some additional clues. Okay, so this includes all the registers as well as RAM. So it's going to narrow down, all the components down to just a few. Okay, so it might be helpful if you have a diagram on your own that has the RAM and all the registers already highlighted. Okay, and if someone is suggesting, but Tech, can't you kind of highlight those items for me in the exam question? The answer is no, because that is not my job. Is that okay? I know, some people may feel, but that's just mean. That is just so mean of you. I don't have a problem of getting labeled. So anyway, so now we go back to the diagram and we're going to do the analysis. Okay, where are our registers? Um, the current time is 9:44. So if you need to revisit this part in the video, 9:44 it is. All right, so we have the program counter, it's a register. We have 4 registers inside the register bank. We have a flags register over here. We have an instruction register here. Um, and that's about it, okay? So those are the registers that can be updated. And then the one other thing that can be updated is the RAM component. So those, I have just enumerated, I have just listed every single thing that can potentially be updated. The ALU, interestingly, it cannot be updated by itself. Okay, it can do calculations, but it cannot remember things. If you give me 2 numbers to add, I'll give you the output, but that output is not remembered. Okay, the next clock cycle, it can be gone, like just disappeared. All right, what about this register down here? Well, since the question is asking about the rising edge, this register is not going to be changed by a rising edge. This will be updated by a falling edge, but not a rising edge. All right, so with that said, yep.
How do we know that it's going to be updated by falling edge instead?
When you click on the component using a select tool, it will tell you that this one is updated or triggered by a falling edge, as opposed to the other ones. Every single other one is triggered by a rising edge.
And how will we have this in the exam? Do we just like print it out and say, hey, these registers are falling edge, rising edges, or?
There's only one that has a falling edge, and that's the microcode pointer. So everybody else are responding to a rising edge.
Okay.
Yep. So that makes it easier to remember because as long as you're looking at anything but the microcode pointer, they all update on the rising edge. RAM updates on the rising edge as well. All right. So what is next? Okay. So now we go back to the question and we ask, look at this. I mean, do I really have to track down everything to find out what is going to be updated? Let me give you a clue. Okay. In order for something to update, there's usually a chip select or an enable that has to be a 1. So I would look for those first, okay? So I'm going to look at RAM select or chip select. It's a 0. RAM is not even paying attention. It's not going to update. Okay, done. Um, we look at RIEN. That's a 1. Okay, so now the context is what does RIEN do in the circuit? So this is where, when people do not do what I suggest to do, this is going to be hard because, it's going to be hard to locate where is RIEN. This is RIEN. It enables this multiplexer, but also goes into the ALU, I mean the register bank, not the ALU, the register bank. So when it does get into the register bank, we want to find out what does it do inside the register bank. So inside the register bank, we can see RIEN, which is labeled as register input select, is the enable or is the select. I take it back. Sorry, I take it back. RIEN is this particular pin here. It enables the decoder. Let me zoom in a little bit because otherwise it's harder for me to click. So this enables the decoder, and when the decoder is enabled, then what it will do is it will turn one of the output into a 1, everything else being 0. Which one turns into a 1 depends on the select. All right? So that means if an input enable is a 1, one of these 4 registers will have its enable input being a 1 because this is output 0 of the decoder, this is output 1 of the decoder, this is output 2 of the decoder, this is output 3 of the decoder. Each one connects to the enable of one of the 4 registers. So that means in the question, if you see RIEN being a 1, that means one of the 4 registers inside the register bank is going to change. Let's see, PCEN is the other one. Okay, the program counter is clearly not going to be enabled, but from the circuit, this is where we find it. So PCEN is right here, and that connects to the enable of the program counter. There's one that is kind of obscure, which is this one over here. This is referring to bit 0 of the D port of ROM. So for this one, it doesn't have a name. You really just have to kind of track it down and find out where it connects to. So we are looking at the D port of ROM. To be more specific, we're looking at bit 0. So it is about this particular wire. It goes to the instruction registers enable. So in this case, the instruction register is also going to update. Is that okay? All right. So getting back to the question, the correct answer to the first part is um, one of the 4 registers inside the register bank is going to update. And which one do you think is going to update? Whichever one is selected. So from this list here, which one do you think is the select of the register that's going to update? RI cell, right? Register input select. It is a 2. So 2 corresponds to which of the 4 registers inside the register bank? It's register C. So register C is one of the part of the answer, and then the instruction register is the other answer. Okay, both of those are going to change. Now somebody may be asking, but this doesn't look like a fetch cycle. Why are we updating the instruction register? Well, just because I can. It's not interfering with what it needs to do. It's just wasting an update for something that is not going to be important. Okay, but nonetheless, the answer is going to have to require both components to get full score. Trace your reasoning to the bits from the data port of RAM. You may refer to these using the names of the pre-dissected microcode. So in addition to telling me that register C and the instruction register will be updated, you have to tell me why you think so. Okay, what values within all of these tunnels is telling you that those 2 items are going to be updated. All right, so I need an explanation. Doesn't have to be very long. You can just say, oh, it's because this one is a 1, that one is a 2, and this one is also a 1. Okay, that is sufficient already. Okay, so the next step is to identify and explain how these components are updated. In other words, you have to track all the way to the source of the update. Who is providing the value to update to each of the components of the first step? So that might take a little bit longer. Okay, so in this case, we have to go back to the tunnel values. So and then we have to ask the question. And the way we ask those questions has to do with the dependency or how things are connected. We already know which 2 are updated, right? We know that, okay, let's do one at a time. We know the instruction register is going to be updated. So which node or which wire or which port of the instruction register should I pay attention to right now if I want to find out how it's going to be updated? It has got 1, 2, 3, 4, 5. It has got 5 ports. It has the D port, the enable port, the clock one, the reset, and also the output. So which port should I track down if I want to find out how it is going to be updated? The D port, very good. So the D port is the one that I need to track down. And this one does go to all the different places. So it does go to the D port of RAM, but RAM is actually not selected. I know it looks selected right now, but in the question it is not. So it is not coming from RAM. And then we continue to look at the selected node, and it goes to a lot of places like the multiplexer, but the input side of a multiplexer cannot output anything. So these 2 are basically dead ends. So that means the only thing that is left for me to analyze is coming out of this demultiplexer. But in order for this demultiplexer to actually output to this particular node, I need 2 conditions. Register output 0 enable needs to be a 1, and we also need register output 0 demux to be a 2. So we need to confirm that. Go back to the question, confirm that register output 0 enable is a 1, and we also confirm that register 0 demux is indeed a 2. So what that is telling me is this node here does connect to this particular input. So the next step is to track down, so what thing inside the register bank is connected to output 0 of the register bank. So there are a few ways to do this. The first way is really to go into the register bank, and then you look at this particular output, and you trace your way backwards, okay? This node connects is the output of the multiplexer. So now you need to ask which input of this multiplexer connects to the output pin. The only way you can answer that question is to look at register output 0 select. So in the question, we have register output 0 select to be a 3, which is a 1 1. So if the select is 1 1, that means input 3 connects to the output, and input 3 eventually connects to the output of register D. Whew. So now we know register D is the source of the update. And then your answer needs to indicate that the instruction register updates to the value of register D inside the register bank, but you also have to explain how you arrive to that conclusion. Now, the way you explain how you arrive to that conclusion can simply be repeating the relevant items on this list. In other words, you just say, okay, because of this, this, and this, and this, now I know these two things are connected. Is that okay? But you have to be precise about what you list, what you include on that list, because I know some people might be thinking, so if I include everything here, I'm going to have to hit all the ones that are actually relevant. Well, in that case, that person is going to get almost a 0 because of the shotgun approach. So I need the answer to be precise, okay? Give me just the items that explains why you think those two components are connected. Is that okay so far? So I'm giving you the grading criteria as we talk about the answer. All right? Yep.
Say that again, I didn't quite catch it.
Okay, so what I said was in order to explain, in this particular case, let me go back to the diagram. So in this case, in order to explain why register D inside the register bank, has a path to connect to the D port of the instruction register, there are several items that should be on that list because they are controlling the multiplexers and the demultiplexers along the way. So your explanation of why instruction register equals to register D should also mention how you figure out that these two things are connected. But some people may be thinking, if I just include everything under the sun, okay, if I just include all the tunnel states, then it would also include the ones that are actually in the answer, right? And I was just trying to say that, no, that is not going to give that person any points, because if I see a shotgun approach, I'm just going to say, well, that person does not know what the correct answer is, and therefore using a shotgun approach, and that would just get a D or an F of a grade. Is that okay? So that's basically what I said. I needed to be precise. Tell me exactly what is needed to explain this connection, but anything outside extra is not going to get any points. In fact, it can get a deduction of the points. I mean, if it's just one item extra, I'm going to go like, well, okay, not a big deal. But if I see everything or a deliberate approach to include a whole lot more than what is needed, then it will be a different consideration. All right, so that's the second part. And then register B is the register being updated, which is register C, is connected basically the same way. But in that case, you also have to, the person, you also have to explain, how this node is going through this multiplexer. So in that case, you will need to explain that RIEN is a 1, RIMUX is a 0, in order for this input to connect to this output here. And then you also have to explain that RI cell is a 2, and as a result, inside the register bank, register C is going to get the content of register D, because at that point, these two registers are connected. The Q port of D eventually connects to the D port of C. So on the rising edge, the content of register D will update the content of register C. Is that okay? All right. So getting back to the question, there's another phase here. How components are connected and which component is connected to which component. Okay, so that's kind of the second part. So the third part is to ask you, does this microcode slice remind you of an existing instruction? So any instruction on the opcode sheet is going to be on the test because we really have finished talking about all of them. So which one do you think is applicable here? Okay, first thing first, okay? From your perspective, it might be helpful if you also include a printout of the opcode table. So let me go to the opcode table, and I'm not sure where it is. Let me see here. Opcode table, there we go. So if you look at the opcode table, I got the answer already highlighted. You are updating one register using the content of another register. So the row that is already highlighted here is going to get the job done because it's copy register. In this case, X is a register, Y is also a register. X is the register that is updated, Y is the register that is providing the value to update. So if I ask you what is the mnemonic corresponding to the tunnel configuration, all you have to do now is to say, well, C is the register getting updated, so C is X, Y is the register providing the value to update, so Y is register D, so the mnemonic of the instruction should be CPR space C comma D. Is that okay? Now, because all of these instructions are within the scope of the exam, so I would advise all of you to be familiarized with all of these instructions. Now, do you have to kind of put these into Logisim and actually see how the connections are made? Maybe, maybe not, okay? But you definitely want to be familiarized with all of the instructions just so that you know, oh, if this is updated because of from that, it's corresponding to that particular mnemonic. The last part of question number 2 is going to ask you to give me, let me see here, the opcode. Okay, so this one is asking you to give me the opcode. So if you go back to the opcode table, this will give you an idea of how to figure out the opcode. So with this particular opcode, 0101 has to be there. Okay, there's no question about it. So all you have to do is to figure out what is XX and also what is YY. XX is supposed to be specifying register C, so XX should be 10. YY is supposed to figure out to specify register Y, which is register D, so it should be a 11. So as a result, the actual opcode should be 0101 1011. And if I read the question carefully, let me see if I specify what base the answer is supposed to be in. So what is the hexadecimal opcode? So that means you also have to convert from the bit or the binary representation into the hexadecimal representation. In this case, it is a 5B. The 5 is because of the 0101, and then the B is the 1011. So this also means that you probably need to know how to do conversion between base 2 and also base 16. So if you already know a technique to do it, if you can memorize the table, that's great. If not, put it on your quote-unquote cheat sheet. This is open book, open notes. You can bring anything that is printed or handwritten prior to the test. Is that okay? All right. So make sure you have all the tools that you need to answer the questions. This is question number 3. So question number 3 is about the double precision floating point number representation. The question is starting with the positive slash negative exponent lab slash assignment. Ask you to write the code in the subroutine E10 to exponent exp2 in order to convert a value represented by a structure as follows. So that structure is exactly the same as it is in your lab. Okay, so this structure has not changed. from the from the lab. The criteria of the output, which is also coming from the lab, is the member coefficient should have bit 63 set. Okay, it should use all 64 bits in the unsigned 64-bit unsigned integer. The value being represented is preserved as much as possible, and as the output, we also want the member E0 to be a 0. Now, if this is all looking boring to you because you already did that program and you go like, yeah, we know what the program is supposed to do. I got it done already. That's good, okay? That is a good sign. On the other hand, if somebody is saying, I have no idea what this is all about, well, that's probably a good indicator to say, I might need to review the solution to both of those labs. Starting with the value V of 54.125, and what base do you think this is in? It's in decimal. It's in base 10 because it doesn't have any special notation to suggest otherwise. I want you to express V in base 10 scientific notation as a string, such as the one used in the positive and negative exponent lab / assignment, where the coefficient is normalized. For example, 9.87 times 10 to the power of 13 is, it's basically what it is, but this particular mantissa or this particular coefficient is normalized. So what would be the answer if I were to ask you to express 54.125 as in a base 10 scientific notation with a normalized coefficient? What would that look like? Well, first, yeah, go ahead.
5.4125 times 10.
E1, right? E1, yep. Okay, so that would be the answer to that question, and I'm going to use my mouse pad to record the answer in this case. So for the double precision floating point number question from Spring 22, which is basically my way of telling you that your question may not be the same, okay? But it still requires you to understand the same stuff, okay? So even though the format of the question may not be the same, you still need to understand what is a double precision floating point number, what is the scientific notation, what is a normalized coefficient, and so on. So in this case, the answer to the first part of the question is simply 5.4125 times 10 to the power of 1. So it's important to use E1 instead of saying times 10 to the power of 1 because the question is asking about the notation of a double in C and C++, okay, as the way that we talk about in class. All right, second question. Second part of the same question is, if this notation is specified on the command line of the positive or negative exponent lab or assignment, what will be the values of the members of the structure pointed to by Pn at the entry point of the subroutine? And this time I kind of messed up because it's supposed to be E10 to exp2. But basically it's asking the question of, at the entry point of the subroutine, what should be the values of all of these members? All right, so what do you think? What should be the sign here? It should be 0 because the value itself is not negative. And what do you think should be the coefficient? Well, you have a few choices, right? You have 5.4125 as the coefficient. You have 54.125 as the coefficient, or you can have 54,125 as the coefficient. So A, B, and C, right? Which one do you think is the correct answer? 54,125 is the correct answer because the program, before it gets to your subroutine, would do the processing, and it has to represent everything using integers. So the correct answer for the coefficient is 54,125. What about E10? The exponent of 10. So now you have to look at the math, right? Okay, this part here is probably, well, I can still use this way. So for the second part of the question, the sign is going to be a 0. The coefficient is going to be 54,125. And then E10, What does E10 need to be in order for the value being represented to be 54.125? First of all, is it positive or negative? It's going to be negative, and how far do you think it has to be negative so that we are still representing 54.125? Negative 3, because we have to shift the binary point or the decimal point 3 places to the left. That is correct. And what about E2? I mean, this is just, it's going to be 0 at the entry point of the subroutine. Very good. Okay, excellent. So now we move on. Depending on the value of the member E10 of the structure pointed to by Pn at the entry point of the subroutine or function, this input should be processed by the positive exponent or the negative exponent code as described in the labs. When E10 to exp2 is about to return, assume the function implements the logic described by the lab assignment correctly. What are the values of the members of the structure pointed to by the parameter Pn? You do not really need to use a computer to figure this out. In the following space, explain how you would do this manually. You can use numbers in base 2, base 10, or base 16, but use the proper notation so there's no confusion. You probably want to use base 16 for the coefficient. All right, so that's kind of a hint. All right, so let's try to figure out the ones that are easy to figure out, and then we'll try to figure out the ones that are not so easy to figure out. Okay, so going back to my editor here, the sign will still be a 0 because we are not changing the sign of the value being represented, so it's still non-negative. Not sure about the coefficient, okay, so we'll just kind of leave it blank for now. E10 is supposed to be a 0. E2 is, we don't know what it is. Okay. All right, so at this point, some people may be thinking, well, this is being done on a piece of paper, so even if I have the code with me from the lab, it will still be really, really hard to follow that code because we'll be writing out numbers up to 19 digits in the base 10, and then your calculator probably does not like that either because most calculators do not have the precision to work with 19-digit base 10 numbers. Okay, so the question is now, so what do we do about this? Well, we do it manually, which means we look at the representation of the value in base 2 first, okay? So the question is, if this is in base 10, how do we convert this particular value, which is currently expressed in base 10, to base 2? This part here is about base conversion. So how do we do base conversion here? Well, we just have to come up with a sum of powers of 2 that add up to exactly 54.125. So all you need to do now is to think about powers of 2. 1 is a power of 2, 2 is a power of 2, 4, 8, 16, 32, 64. On the other side, we have 1/2, 1/4, 1/8, and so on. So think in those terms. Do we have a 64? Obviously, no, right? Because 54 point something is less than 64. We don't have a 64. Do we have a 32? Yeah, I would say we have a 32. Do we have a 16 after taking care of the 32? Sure. And that will add up to what, 48? So you have 6 left, right? A 6 has a 4 and a 2. And then what else do we have? What is 0.125? That's definitely not a half, so we have 0 of halves. That's not a quarter either, we have 0 of quarters, but that's exactly 1/8. So we have 1/8 also here. Are we doing okay so far with this breakdown of representing 54.125 using just a sum of powers of 2? Is that part okay? All right. Let me turn off the line number because that's actually causing more confusion. There we go. It looks a lot better now. So now we have to look at 32 and say, how do we represent 32 as a base 2 number? So the trick is if it is 2 to the power of 5, then it is 1 followed by 5 zeros in base 2. 1, 2, 3, 4, 5 in base 2. What about the 16? Well, 16 is 2 to the power 4, so in base 2, it is 1 followed by 4 zeros. What about the 4? It is 1, 0, 0, because it is 2, because 4 is 2 to the power of 2. And then what about the 8th? Well, the 8th is not going to be, it's going to have a point, okay? So the question is, what is, oh, I forgot one thing, I forgot the 2. So the 2 is a 1, 0 in base 2, because 2 is 2 to the power of 1, so we still have 1, 0 on the right-hand side of the 1. And then we have the 8th now. So the 8th is going to be a negative power of 2. So the question is how many, what is the position of that 1? So now you have to kind of think, well, what is the point of the point? And that is actually not intended as a pun. The point of the point is a separator. What is it separating? It's separating the power to the base to the power of 0 from the base to the power of negative 1. Is that okay? So that means whatever is here is telling me the number of halves, don't have 1. And then the next one is the number of quarters, don't have 1 either. The next one is the number of eighths, got 1 in base 2. Are we doing okay so far with how I converted the power of 2's in base 10 into their base 2 representation? All right, so all of this here is based on base conversion. And now we have to do the add. So the adding is pretty easy because we have up to 1, 1 in each column, which means carrying is not a problem. So that becomes the answer in base 2. And then people will be looking at this and go like, okay, but we are not anywhere close to what the answer is supposed to be. Well, we are much closer now, okay? Because now what you need to do is to say, this is kind of the useful answer, but we kind of need to kind of shift this binary point a whole bunch of places. Is that okay? So that means, if I look at this, 110, 110, 0.001 in base 2 times 2 to the power of 0, that's representing V that we need, but it's not in the representation that we want. All right, fine. So if we just kind of shift that binary point to the right-hand side by 1, then we are one step closer. But to compensate for that, we also have to change the power of 2. So are we supposed to increment or decrement it by 1? So by shifting the point to the right-hand side by 1 place, we are doubling the value of the coefficient. So what do I need to do with the exponent of 2 to compensate for that doubling? Do I add 1 or do I subtract 1? Sorry? If you add 1, that means we're also doubling, so we end up quadrupling the value being represented. Well, since it's not add 1, subtract 1. That's right. All right, so this has to do with math, okay? This is about math, and computer science is a branch of mathematics. So, all right. This is going to be kind of boring because now I have to shift it a whole bunch of places. But before I go to that place, 1, 2, okay, yep, okay, so 0, 0, 0, 1. If I get the point all the way to this place here, what is that going to look like? 2 to the power of what? In other words, I'm asking, how many times do I have to shift the point in order to get to this place? 3 times. So that means it's 2 to the power of negative 3. And you go like, well, that's very good, Tech. We got 9 bits out of 64 done. So what do we do for the other 64 minus 9, which is 55 bits? Because what do we want the coefficient to look like? We want it to fill up 64 bits, right? So far, we have filled up 9 bits. So what do I need to do to fill up the rest? We pad zeros on which side? The left-hand side or the right-hand side? I want bit 63 to be a 1. I want to use all 64 bits within the unsigned integer. So where do I pad the zeros? Do I pad the zeros on the left-hand side or do I pad the zeros on the right-hand side? I need bit 63 to be a 1. On the right-hand side, very good. Okay, so that means, I need this to become 110, 110, 001. Do you guys really want me to count to 55? It's actually easier than it seems. 1, 2, 3, 4, 5. So we got 5 already taken care of. So I just have to paste this 10 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Cool. Times 2 to the power of what? I just padded 55 zeros. So what happens to the power of 2? It was 2 to the power of negative 3 before, and now it's going to be 58, negative 58. Yep. So now it becomes 2 to the power of 50, negative 58. And we are pretty close to the answer now. Okay. So one thing you can do is to double check. Okay. You can actually check this to see if the calculation all works out. Especially if you have a calculator that can handle base 2. But then to really enter this into a calculator, you will have to enter 64 zeros and ones. Yeah, good luck with counting. Because I know for sure that I'm going to miss one digit somewhere. All right. So let's see what the question is really asking, because this is getting close to what the question is asking. So the question just wants every single thing here to be filled. So I think we are really done here, because now you can say the coefficient is just this. If you want to do it in base 2. And remember, you are going to be handwriting this. So if you say, no, this is insane. Writing this in base 2 is really insane, then you might want to consider doing this in hexadecimal. But one thing you know for sure is E2. E2 is just negative 58. That's the easy one. So now let's go ahead and see whether there's a more reasonable way to write out the coefficient. So for the coefficient, if you want to convert it into hexadecimal, that means you break it up into chunks of 4, right? So only the first 3 chunks are meaningful in any way. The rest are all zeros. So now you look at 1101 in hexadecimal. You have to find out which digit it corresponds to. So once again, that conversion table can come in handy, unless you have that table already memorized, like I do. So this is a D, and then the 1000 is an 8. The other 1000 is also an 8. And then we have the rest being zeros. So now the question is, how many zeros do we need? We have just taken care of 12 bits out of the 64. So how many additional zeros do we need in base 16? Or you can also flip the question and say, I will need 64 divided by 4, which is 16, base 16 digits to make up the 64 bits. 3 of them are taken care of. So how many additional hexadecimal digits do I need? 13, exactly. So I think I can manage 13 zeros even in handwriting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3. There we go. So copy and paste here. And don't forget that you have to start with a 0x prefix because it is in hexadecimal. So now we have the answer. In other words, I bypassed the entire algorithm thing and came to the answer without having to run the algorithm. The reason why I can do this has to do with the value that I chose. Because the value that I chose, which is 54.125, is easy to represent in base 2. If I had chosen something that cannot be represented in base 2 without repeating, patterns of after the decimal point, this would have been an insane and crazy exercise. All right, so that's the entire exam 2 from spring 22. And once again, I'm not going to guarantee any resemblance of your exam to the one in spring 22. But knowing that, and also text tends to be lazy, you can probably expect certain resemblance to this exam, but it's not going to be exact. Is that okay? So it is not about being able to remember all of the techniques that I used here in this particular sequence. It is about what do I need to know to figure this out on my own. So you definitely need to kind of revisit, first of all, your propagation changes, what the gates do, what is an and, what is an or, what is a nor, what is an and, what is not, okay? How do we do those two steps, the NC versus the PD, and how do we update the table? Okay, that's for question number 1. Question number 2 means you have to really thoroughly understand the processor. So understanding the multiplexers, demultiplexers, registers, RAM, the decoder, all of those are important. And if you're familiar with how things are routed, that will really help speed up the way you can answer the questions. So it's not a matter of can you do it? It's a matter of can you do it effectively in the exam. Okay? So that means knowing where things are and what each tunnel does to each thing is going to be important. You can try to figure out all of that in the exam. Okay? But that's going to use up a lot of time. If you study and get familiarized before the exam, that will make it so much faster. You look at this thing here, go like, oh, yeah, I know exactly where this goes, and it's going to affect that particular multiplexer or this particular demultiplexer and so on. That's going to help you speed up the way you can answer the questions. Um, for question number 3, which is about the double precision floating point number format, that one is about concept, right? It's about the math concept. How do we represent a value using a scientific notation? Now, it can be a scientific notation in base 10, but it can also be a scientific notation in base 2. It's the same concept. You have some kind of a coefficient times 2 to the power of something times 10 to the power of something. So it's just a matter of how do I shift those powers around by adjusting the coefficient so we end up with a particular pattern that we want. So that one is about math. Base conversion is going to be important. Okay, so I just demonstrated how to do base conversion here. In your answer, this would be sufficient. If you want to explain to me, because I'm going to ask for that, I'm going to look for that, okay, so how did you do this? Well, this would be sufficient, okay? I broke down a value into a sum of powers of 2, okay? And therefore, that helped me find out what is the binary representation of a value. Is that okay? Yep.
But 55 zeros, are you actually going to count them, or are you going to trust them? Put negative 58 or whatever.
I probably want to put a clock, when I grade. If it takes me more than a certain amount of time to grade a particular exam, I will start to take off points. Kind of like a taxi, when the taxi is idling, that thing is going to take, so I'm going to give everybody like a certain amount, like if it's within this amount of time, it'll still be okay. I'm just kidding you. I'm just yeah. So if you put in all the zeros, if you put in the time to put all the zeros in, I'll put in the time to count your zeros.
I'm not even sure how I'm gonna finish all this in what, an hour, 2 hours?
No, 80 minutes, 1 hour and 20 minutes. But as I said, this one was not designed for being answered by hand. So yours will be more customized, to be for a paper and pencil type of exam. This one was online, so people were able to copy and paste, use spreadsheets and whatnot. yours is going to be on paper, you will still be using, you can still use a scientific calculator, to confirm the answers and whatnot, but you cannot use a computer, an iPad, or a laptop, or your cell phone. Yep.
In the case of the zeros, just to make sure, can we put like 55 zeros instead of writing them with just a keyword?
Yeah, you can indicate that there are 55 of them, but then you have to tell me where it starts.
Okay.
So which portion has the 5 zeros? Yeah, so that would be fine. Okay. In other words, okay, let me just be clear about, let me be clear more, about what I said is okay. Okay. So what I meant is to say, if you just say, in this case, 110, 110, 001, and then you have 00000 here, and if you do something like this, that there are 55 of those, then I'll still accept that as an answer. So that makes it easier, right? It makes it easier to express it. Yep. Yep.
Can you save this Zernal file something? I kind of want to like look at it later.
All right, so I can export it as a PDF. And let's see, where am I going to export it to? All right, so I just saved it into a file. And let me go back to the browser and go back to, all right, so here we have the announcement. Let's see, go back here. And so I'm going to send it to you guys using an announcement. And the topic title is going to be Follow the Rainbow. So this is the PDF corresponding to Q1. And I cannot remember the name of the file that I saved to. All right, so let's. Sorry?
And there's so many files too.
Yeah, because I haven't reset the computer for a while. And I can't see the bottom because the screen doesn't show. Oh, it's just rainbow.pdf. There we go. All right. There you go. So now you have that PDF.
Thank you.
But it's a PDF, it's not Zerno anymore, so that means you cannot make further changes to what I put in already. Mm-hmm. All right, so you got a week, which means on next Tuesday, if you have any questions about the concepts within the scope of this exam, you will still be able to ask questions for one more class. I always allow one additional class meeting if I can, so that people, who after studying, they go back and go like, okay, I still need some further explanation of this concept. That's what next Tuesday can be used for. And also, the lab is starting now. I do not have a structured lab for you guys to do. So if you want to stay and just continue to talk about these topics, you're more than welcome to. And then at 10:30, there will be the presentation of, how to deal with the pressure and anxiety of a final exam. So, you guys have more than sufficient time today to attend that particular meeting if that is what you want to do. Is that okay? All right. So I'm going to stop the recorder because I'm not planning to lecture any further, but I do have time to answer questions if you guys have any questions about the stuff that we just talked about.